Okay, students, in the next part we are going to look at some concepts that are related to the matrix now, right? And the first one that we are going to talk about is the condition number of a matrix. Okay, so often, as we know, we are interested in solving systems of equations Ax equal to b, right? Important to remember that for us, so in Ax equal to b, when we write that, we actually mean that A is given to us and b is given to us and we want to find x. Okay, A and b are both given to us and we want to find x. Typically, it's important for us to remember that these matrices A and b have real entries. Real entries typically have infinite. When we talking about them abstractly, we're talking about them having infinite precision, right? But in practice, that's not going to happen, right? I mean, the entries A and B are going to be stored to finite precision, right? More than that, even in many situations, B is actually a measurement. In many, but not all situations, B is a measurement. A may be a fixed matrix, right? And A may be a nice matrix with a lot of structure. Sometimes, but not always. B is usually obtained from some measurements, right? And these measurements could have some noise in them, right? And it's noise meaning that the measurement that you get may not be actually the true value, but due to various artifacts in measurement or due to other reasons, you actually measure that something that's slightly off, something that's randomly perturbed from the true value. Okay, so what you have here is not B but B plus delta B. Right, you don't have B but B plus delta B, right? So this algorithm that typically is supposed to take A and B as input and give X as output, right? Now takes A and B plus delta B as input and is supposed to give some output, right? So the input, remember, has changed. It's been perturbed slightly because of these measurement artifacts, right? Typically, we must also say that even A is perturbed, right? Even A will have some difference, A plus delta A, due to finite precision. But we are going to ignore that, right? We are not going to worry too much about that. We'll only worry about the perturbation in B. Okay, you can do very similar analysis when you have perturbation in A also. Okay, right? So you have some perturbation in B. Okay, so you read D plus delta B instead of B. My goal is then that you don't actually measure X, right? But you will actually measure maybe X plus delta X. Right, so the algorithm output will actually be X plus delta X and not X. Okay, because the input has been perturbed, it's natural to understand that the output also must be perturbed. My goal is to understand how much the output has been perturbed. Okay, in particular, we do not want the perturbation in the output to be way more than the perturbation in the input. Okay, in something like that, right? I mean, you don't want the relative perturbation in the output to be way more than the relative perturbation in the input. Okay, of course, perturbation also is, so what we're going to look at is we're going to look at the relative perturbation, meaning that we'll take norm of delta X by norm of X. Okay, so remember, X here is a vector, delta X is a vector, corresponds to how much the output has changed once your input has been perturbed. I'm going to be interested in this relative quantity, delta X by X, right? And this is what is my input relative perturbation, delta B by B, norm of. You can pick any norm here, of course, depending on the scenario, 2 norm or 1 norm. By the way, which norm to pick is very confusing, right? Like, why are there so many norms? Like, does it really make a big difference which norm I use? Does it really make a big difference whether I use 1 norm, 2 norm or infinity norm or spectral norm or something else? It does actually. It makes a tremendous amount of difference. You will see as you go through more courses in your curriculum that lot of modern research, in fact a huge subfield of signal processing is driven completely by using a different norm for solving signal processing problems. That's very crudely speaking, but that's how it worked out in the end, right? So this is the relative error in the output, this is the relative error in the input. Okay, so typically when nothing is mentioned, you just assume 2 norms. So these are 2 norms here, right? But for now, just for the sake of keeping my discussion general, let me just assume an arbitrary norm here, right? So how is the relative error in the input related in the output? How does that compare to the relative error in the input? That's what I'm interested in, right? In particular, what I want ideally is I don't want this to be too much bigger than this, right? I mean, the input has some error, so I definitely can't escape some error in the output. Output will also have some error, meaning some perturbation, right? But I just don't want the perturbation to go out of control. We discussed a little bit of this even in the initial, even in the initial segment also, right? We'll just try to formalize that concept here, right? So we're very much interested in comparing these two. Okay. Fine. So to do that analysis, let's first try to see how X is related to B, right? And we already know the answer to that. Let me just assume A is invertible, right? For simplicity's sake, we'll assume A is invertible. Otherwise, we know this may not even have a solution, or what not, right? Just assume A is invertible. Okay. So then I know how X is related to B. So X is simply A inverse B. Okay. This is what I have been calling as the input, and this is what I have been calling as the output here, right? X equal to A inverse B. So when you have A inverse B plus delta B, perturbed input, you are getting a perturbed output, X plus delta X. Okay. Perturbed input results in perturbed output, right? So what is this, delta X, right? So delta X is just A inverse delta B. Okay. So let's try to now use this to compute the, relative error, right? So norm of delta X, right? Here when you take the norm of delta X, that's the same as norm of A inverse delta B. By norm of X, correct? By norm of X. Okay. So I want to compare it to, however, so remember, I want to compare it to norm of this quantity over here, right? So let me just artificially try to introduce that. Okay. So I'm just going to add a term here, norm of B, okay, and I multiply by norm of B here. Okay, we'll see in a minute how that would help. Okay, fine. So this norm of A inverse B over here, this quantity over here, norm of A inverse B, I just know that it is bounded by norm of A inverse times norm of delta B. Okay, by norm of X into norm of B, okay, times norm of B. Okay, fine. So that's what. So here is where I have used the inequality that I discussed before, right? We already did that when this is 2 norm, right? When this is 2 norm, we did this inequality, right? The norm of any matrix times a vector is less than or equal to the norm of a matrix times norm of the matrix times the norm of the vector, right? This works for any induced norm, right? So here you can just pick. So this norm here is going to be the induced norm corresponding to the vector norm that you started with. Okay. As I said, safest thing, just assume 2 everywhere, then all this will go through very easily. Okay. So now this quantity over here is the norm of A inverse, right? And you already got this term over here that you wanted, right? You wanted to compare this quantity to this quantity, right? So you already got this term over here. So whatever is left is this one, norm of B by norm of X, right? But what is norm of B by norm of X? Right? Norm of B by norm of X. B, remember, is just AX. It's norm of AX by norm of X. And that is by definition again less than or equal to norm of A. Correct? So what we have here in summary is this. Norm of delta X by norm of X. The relative error in the output is less than or equal to norm of A inverse times norm of A times norm of B by norm of delta B by norm of A. Okay, this is what I am able to derive, right? So what you have here on the left side is the relative error in the output. What you have here on the right side is the relative error in the input, right? And this quantity over here is the factor, right? Is in some sense the error amplification factor in some sense, right? So the idea is that if you know this quantity is small, then you can claim that this quantity over here, the relative error in the output, so I'll just write it down, output error, let's call it input error. if this quantity over here is small, then you can say that the output error is not too large, right? Output error is less than or equal to some small factor times the input error. Okay, fantastic. So how small can this be, right? So what is the norm of A? So if well, so far the analysis doesn't rely on any particular norm, but right here let me just assume spectral norm, right? So norm of A is just sigma 1 of A, largest singular value. It's norm of A inverse. Well, what are the singular values of A inverse, right? The singular values of A inverse are the reciprocals of the singular values of A. Correct? So singular values of A inverse are 1 over sigma 1 of A, 1 over sigma 2 of A, so on. You go up to 1 over sigma min of m comma n A. Okay. So here in this case I am assuming A is square, right? Because that's why I am writing A inverse and all that. So here you don't have min of m comma n, I'll just write sigma n. Sigma n, right? In singular values, which of these is the largest? This will be the largest, right? Because sigma n A is the smallest, right? So when you write singular values of A, you'll order them like this. Sigma 1 is the largest, right? So on, and you go up to sigma n. Okay. When you take the reciprocals, this becomes the largest, right? So this is equal to 1 over sigma n of A. Okay. So this factor over here is actually equal to sigma 1 of A by sigma n of A. Or in other words, it is the largest singular value by smallest singular value. Okay, largest singular value by the smallest singular value. Okay, so that's what this quantity is. That is called the condition number of A. Sometimes it's written kappa of A. Okay, the Greek letters of kappa. So kappa of A is the largest singular value by the smallest singular value. Okay, so the condition number tells you how much the errors get amplified, right? How much errors, in some sense, how much are the errors feeding forward, okay, going forward. Okay, so the output error, the output relative error to be precise, is less than or equal to condition number times input relative error. Okay, if the condition number is small, then the output relative error, okay, how small can the condition number be? Like, what is the smallest possible value of the condition number? It's 1, right? It cannot actually be below 1. Right, you see that, right? It cannot be below 1 because because of the very way here is the largest by the smallest, right? Smallest it can be in 1, which makes sense, right? So if the condition number is 1, right, then that means that the output error is less than or equal to the input error, right? Which makes sense. In fact, you don't expect the output error to be less than or equal to the input error, right? If the condition number is 1. Okay, if the condition number is higher, let's say condition number is 100, then you can say that the output error is at most 100 times the input error. Okay, I cannot actually say more than that, right? So if you know the input error to be like 0.1, the input relative error to be like let's say 1%, right? So if I know the input relative error, let's say for the sake of sanity 0.1%, right? That means I know that it is 0.1 over 1000. Right? The input relative error is 1 over 1000. Then if the condition number is 100, then you are saying that the output relative error is like 10%. Okay, is less than or equal to 10%. I cannot say more than that. Right? It may actually be smaller than that. Okay. In general, this bound here is quite tight in the sense that you can actually generate input and output directions for which the output error happens to be as large as this right quantity. Right? So output error is 10% for an input 0.1% error, which is pretty bad for condition number 100. Right? If the condition number was just 1, the input error is 0.1%, output error is also 0.1%. Right? So if the condition number is small, errors don't carry forward. The condition number is large, errors keep getting added up. Okay. Okay. So which are the matrices that have a very large condition number, right? So if the condition number is large, we look at this quantity here. If the condition number is large, that basically means that the denominator is very small compared to the numerator, right? So that means sigma n is close to 0, right? Effectively speaking, close to 0, then condition number is high. What does this mean? Sigma n A is close to 0. Sigma n is close to 0 typically means the largest singular value is very small. So remember, I assumed A is invertible here, right? If A is invertible, all singular values are non-zero. However, they can be very close to 0, right? What this is saying is that if the singular value is very close to 0, then the condition number is very high, right? Meaning that, well, intuitively, if the singular value is close to 0, then effectively the matrix is close to being non-invertible, right? It's close to being non-invertible. Okay. So that's the fundamental idea here, right? So if you have a very small singular value, then effectively what's happening is, when you look at the matrix interpretation as a system, right, the singular vector Vn Un corresponding to the smallest singular value, it gets multiplied by sigma n times Vn, correct? So basically here what's happening here is that the output gets attenuated quite a bit, because sigma n is very close to 0, meaning that whatever the input is, right, the output gets attenuated a lot, quite a lot here, right? So naturally, whenever you're trying to reverse engineer, meaning you're trying to find the input from the output, right, even a small error here could potentially have a huge corresponding pre-image over the input side, right? Because the output itself is very small, right? So the output amplitude levels you're looking at itself are very small. So if you add a small error here, right, it's not clear if that's coming due to a huge change in the input, or if it is coming due to a noise in the observation itself, right? So that's the main idea. So we'll continue from this in the next talk. Yeah. So just to here finish this up. Basically, what we are saying here is that if given any input direction, the output is multiplied with sigma n, which itself is a very small number. So the output values you are dealing with here are very small, right? So if you add any small noise, it's not very clear if that is due to a huge change in the input or otherwise. Okay, so this leads to essential non-invertibility in the system, so to speak, right? Okay. It's very clear if you actually take the sigma n over here, you'll get 1 over sigma n. So basically what will happen is that you have to multiply whatever you get with 1 over sigma n to get to the input, right? If sigma n is small, you end up multiplying by a very large number, right? So any noise ends up getting amplified. Okay. So that's the main idea behind the condition number, right? So what are the matrices that have the smallest condition number, right? This said the smallest condition number that you can get is 1. What are the matrices that have the smallest condition number, right? So if you need a condition number of 1, right, it means the largest singular value must be equal to the smallest singular value, right? Which means all the singular values must be equal, right? So condition number equal to 1, that means kappa A equal to 1 means all singular values must be 1. Okay, when does that happen, right? So if you remember U sigma V transpose, if all the singular values are 1, essentially you get a product of orthogonal matrices. That means you get an orthogonal matrix, right? So it happens A must be orthogonal. Okay, for an orthogonal matrix, all singular values are 1, right? Because A transpose A is just identity, right? So the eigenvalues of A transpose A are just all ones, correct? So singular values are simply all ones. Okay, and we have seen this before, right? Orthogonal matrices don't carry error forward because they preserve the norm, right? We discussed this in the very first segment, correct? So in general, the condition number is a very fundamental property of a matrix that relates to how well your system will behave with noise or with fixed floating point errors and so on and so forth, right? So we say a matrix is well conditioned if the condition number is small enough. We say the matrix is well conditioned. We say a matrix is poorly conditioned if the condition number is large. Okay, typically we want condition number to be fairly small for most applications.